Good morning, everyone. For today's class, we will talk about logic statements and quantifiers. So this is connected to the lesson that we talked about last time about deductive and inductive reasoning. However, logic here is a more general concept because we can divide logic into four. We have this formal logic, informal logic, symbolic logic, and mathematical logic. So the deductive, inductive reasoning, remember, deductive reasoning, what is that? From general to specific, right? And then the inductive reasoning from specific to general. That's under the informal logic. The formal logic has to do with deductive reasoning and certain syllogism, but we will not tackle that, okay? These logic statements and quantifiers, they fall more on this topic of mathematical logic and symbolic logic, especially the symbolic logic, because you will see some symbols here, okay? So as the word logic or logical, so it still has to do with reasoning in a way, no? Or argument, prepositions, okay? Now, just like what we've been doing for the past weeks, we always start with the keywords and key phrases. But before that, we can divide this lesson into two parts. So part one has to do with logic statements. Part two has to do with quantifiers. So under part one, logic statements, these are the keywords and key phrases. But of course, you have logic statements. That's one of the keywords and key phrases. You also have simple statement. So can you write them down? Compound statement, and leave spaces so that later you can write details in those spaces, okay? And then we also have the truth value. Can you write truth value? And then also truth table. If there's truth value, there's truth table. And then we have logical, can you write this? Logical connectives, or yeah, logical connectives. And then, or logical operators. We also call them logical operators. And then we have this statements, this types of statements. The negation. Can you write negation? We have a lot actually. There's something different in this lesson today. Unlike before, there's just few. But what we have is a lot of computations, right? And for formulas, whereas here we don't really have formulas since logic, right? But we have a lot of keywords and key phrases, just like in part one. There are a lot of them. So what else? So we have negation. So can you write them down so that you know what to focus later on? Negation, and then conjunction, disjunction. So conjunction, disjunction. What else? Conditional statement. We also have biconditional statement. Okay, class. And then for part two, yes, we have quantifiers. No, quantifiers. So here we just few. Yeah, the word quantifiers. If we have logic statement, there's what you call quantified statement. However, you will not see this in this, just the concept of quantified statement, but not really this phrase quantified. If it's in part one, we have statements. In part two, we also have statements, and we call them quantified statements, and we use quantifiers there. Unlike in part one, we use in the logic statements, we use the logic, what do you call this? The connectives. Okay, so there's like analogy, right? There's an analogy there. Whereas in part two, we use quantifiers in quantified statement. In part one, we use connectives in logic statements. Okay, what else do we have? We have the, what do you call this? The universal quantifiers. So can you write universal quantifiers? And universal quantifications. See, we have a lot of terms. And then we also have existential quantifiers, and then existential quantification. So at the end of this module, you're expected to distinguish between simple and compound statements. Remember, I mentioned that in the keywords, key phrases. Write compound statements in symbolic form, and vice versa. Use quantifiers appropriately. Okay, class? Let me just mention to you that we can connect. Somehow, there's a similarity in grammar. Remember grammar in English. You remember simple sentence, compound sentence. Remember those, class? So there's kind of similarity. I want to connect it so that you won't find the lesson abstract. I want to link it to what you know already, but in different field, not mathematics, instead in grammar. No. So I believe you know what simple sentence is. No. Compound statement. Remember, we have those compound statement. Compound sentence, you connect two simple sentence, right? Two or more simple something like that. I don't want to mention the other terms because this will become English class instead of math class. Those terms like Independent clause, dependent clause. Okay, I don't want to mention that. I just want to mention that there is a similarity. Like, for example, in compound sentence, we have two simple sentences or compound statements, right? Two or more. So there's similarity, something like that. Except that we will have symbols here. But not only we will convert the statement into symbols. That's why this is symbolic logic also, right? But since there's this is mathematics, we use mathematical logic. Okay. Underlying, somehow you can still apply those reasoning, the deductive, inductive reasoning. Somehow behind the process, you will apply this specific to general, reasoning, general to specific reasoning. Okay, anyway, so just to connect it with those, and then you remember in the sentences, we also have what? Declarative. Remember those? The kinds of sentences in English, in grammar. Declarative sentence, interrogative. Remember? Interrogative questions. And then we have the imperative sentence, command or request, interrogative. So somehow this is related to declarative sentence, okay? The declarative sentence in grammar. Okay, just to give you an idea of what you will learn today. Similar. I want you to connect to those concepts. They have similarities, but there's more about it because we connect it to mathematics. Okay, class? Especially this symbolic and then quantifiers. Okay, so let's focus now on one concept. So let's start the part one. So what's part one again? Logic statements. What part two? Quantifiers or quantified statements, right? Okay, part one, logic statements. Okay, so first we define. Remember, we started with keywords and key phrases, but you don't know the definition. So I mentioned to you to leave spaces. So you can write, you don't have to write this whole thing. Based on your understanding, you can write some words there. Okay, so what is logic statement? So as I mentioned, logic statement is like declarative sentence in grammar. That's why it's mentioned here, declarative. But it's more than that. It refers to a statement that's either true or false, but not both true and false sentence, which is declarative. So when you see an example of logic statement, it's really a sentence. No, it's really a sentence, declarative sentence. She's beautiful, something like that. She's ugly. Today is Monday. Those are something like that. Okay, because you can tell whether it's true or not. For example, today is Monday. True or not? True. Today is Monday, right? So that's a logic statement. If I say today is Wednesday, oh, that's a logic statement. And it's in English, in grammar, that's also a declarative sentence. And that's also a simple statement. Okay, let's define simple statement mathematically later. So you understand? So there's similarity to what we learned na before in grammar. Okay, and also in deductive reasoning, right? So today is Wednesday. Of course, that's false, right? Okay, so we connect that. That's something different here in the logic statement. We try to validate whether it's true or false, not just statement, declarative, but we connect it whether it's true or false. Okay, so it's a declarative. So if it's a declarative class, it's not interrogative. So if you have interrogative sentence, what's the time today? It's not a logic statement. What is the time today? It's not. If it's a interrogative sentence or question, if it's imperative, I mean, command, do this. Oh, it's not a logic statement. Okay, class. So it's only the declarative sentence, which is, or statement, which is a logic statement, because you can validate whether it's true or false. Okay, that's logic statement. And we have two kinds class of logic statement: the simple statement and the compound statement. But again, as I mentioned from the during the introduction, or overview, this is similar to the simple sentence, compound sentence, or simple statement, compound statement also that we learned in grammar in English. Okay, but of course we will not mention terms here that we use in English, like dependent, independent clause. We will not mention. So but there is that kind of syntax or structure in the sentence. There's similarity in the structure, in the syntax. When you see the simple statement, which is a logic statement, or a compound statement, which is a logic statement, you can see similarity in the syntax or the structure of the simple statement or simple sentence, compound statement or compound sentence in grammar. There's similarity. Okay, later you'll see that when we go into the next slides, the following slides. So simple statement is a statement that gives a single idea. Single idea. Okay, just like what I mentioned a while ago. Tomorrow is Tuesday. So that's a single idea. Okay. Compound statement, it's a statement that reveals two or more ideas. So here you will see really the similarity in compound sentence. For example, this is a a compound statement, which is a logic statement. Today is Monday, tomorrow is Tuesday. So that's a compound statement because you use the word and. Remember in English, if you use those what do you call this? Remember the fanboys in English, fanboys for, and, neither, but, or, yet. So fanboys. And you connect two simple sentences using those fanboys. We have compound statement or compound sentence. So similar to this one, there's a similarity, except that this time we will convert it to symbols. We will use symbols. That's why this is symbolic logic. Okay, class? So I believe you were able to connect it to your past lessons in grammar. Okay, class? So now let's go to more details of this. Oh, the game is not yet here, class. We haven't started the game yet. There's a game here. It's like game is like a puzzle, right? So anyway, so there. So I mentioned to you about the truth value. So truth value of a simple statement. So as I mentioned, your simple statement can either be true or false. So we can talk of truth value of a simple statement. It's simple as that. That's the meaning of truth value. We can also talk of truth value of a compound statement because it can either be true or false, right? For example, my example a while ago, today is Monday and tomorrow is Tuesday. So what do you notice? Today is what? Today is Monday, true. Tomorrow is Tuesday, is also true. So logically, if you will think logically, you know, the statement is true, right? True. What if I made, for example, I made my first simple statement as today is Sunday. So we know it's false, right? It is false. Today is Monday. Today is Sunday, false. And, so I will use the word and tomorrow is Tuesday. The second simple statement is true. So what can you say about the whole sentence, the whole statement, which is a compound statement? That's what we will study today. What can you say about it? Is it still true or false? Because one is false, the other is true. So what can we say? That's our goal today. How do you analyze that? That's for me, that's a game. Okay, it's like a game. Okay, so that's the game actually, you know. And there's more to it. It's not as simple as that. There's more to it. Because we will talk about truth table. In truth table, that's a strategy class. In a way, class, we have here like a problem solving also, but not really the usual problem. No, not like that. Because here they are in symbols. They are put in symbols. But in a way, we have to understand it also, so that we can do that step 2 in problem solving, which defines strategy. But we're given a strategy here already, which is the truth table. Remember, in our past lessons, the strategy are the formulas and so on and so forth. We're given already the strategy. Here, the strategy to solve that problem, which in symbols, in symbolic form, we use truth table. So here, class, as I mentioned, it's not as simple as answering it as true or false. In truth table, you'll be answering a lot of these statements. You have to answer whether it's true or false. But it's always like that. It's always binary. Is it true or false? Something like that. And the statements in class, we don't really write this. For now, we generalize it. We use letters. In this class, we use capital letters. But for other resources, they use small letters. Okay, you'll know that later. So truth table, it's dependent about the truth value of a compound statement for all possible truth values of simple statements. So you notice, usually we use a truth table for compound statements. That's why truth value of a compound statement. But we know that compound statement consists of simple statements. So in effect, we also have to get the truth value of the simple statements. You'll understand this better with an example class. Okay, later. But for now, we still need some, we have to study first the other terms, remember? The keywords and key phrases in part 1. What else? We have the logical connectives and symbols. This is similar class to the fanboys. Remember the fanboys that I mentioned to you in English, in grammar? Fanboys. But of course, there will be a difference, of course. But the end is there, right, in the fanboys, the or. But the if then, if and only if, it's not fanboys anymore. Okay, but what I'm saying is there is a similarity. Okay, so now what is a logical operator or connective? On mathematical statements is a word or combination of words that combines one or more mathematical statements to make a new mathematical statement. Okay, so in other words, we use these logical connectives and symbols to form a compound statement. Compound. So for example, if the statement is denoted as P and the other statement as Q. But you notice here small letters, because sometimes small letters, sometimes capital letters. Okay, class? But this should be small letter. For example, if you have a statement P, so how do you use this connective, not P? For example, today is Monday. That's true, right? I can say today is not Monday. That is false. So how do I put it in symbols? So today is not for example, P. P is today is Monday. What is not P? Today is not Monday. So how do I put it in symbol like this, symbolic form like this? I'm sorry. The symbolic form will be like this. Okay, so you don't really write the statement, but you just let P be today is Monday. That's true. But if I put, if I want not P, so I will say not P, right? Today is not Monday. That is false. So what's the connective not? How do you put it in symbolic form like this? You don't really have to write the statement because you already know that P is, what's the meaning of P? Today is Monday. So what's the meaning of this? Tilde. We read this as tilde P. This symbol, negation. So that means today is not what? Today is not Monday. And what's the truth value of that? False. What's the truth value of the P, the statement P, which is today is Monday? True. Something like that. Okay. So that's negation. And then the rest we have and. So again, we have statement P, statement Q. Like for example, statement P, today is Monday. Statement Q, tomorrow is Tuesday. Something like that. How do you put it in symbols? You put it like this. P, I think this one is caret symbol. P caret Q, something like that. And we call it conjunction. So now you know already the meaning of conjunction plus negation. These are all what? Compound statements. Type of compound statements. Negation, conjunction. And then for the or, so that's it. We use this symbol. I think we read this as wedge. P wedge Q, disjunction. And then the if then that you know, class, the if then statement that you know already. So we have here if then blank. Okay, we have example later about that. Then this is the symbol. Okay, conditional. And then if and only if. Okay, there. By the way, class, we call the if, this is an additional knowledge, the antecedent, and then the then part, we call it the consequent, something like that. Okay, but you don't really have to memorize them. Okay, let's have examples. So there, for example, this statement, it is raining. The Q, Daisy is playing golf. So it's simple as understanding as, if you have this symbol and you know that statement P is this statement, you know already, and Q. So meaning to say, if you have this statement, if you see this symbol, you know the meaning is, it is raining and Daisy is playing golf. Because the symbol for and, remember, and is connective. The symbol for this connective or this logical connective, what's the other term? Or operator? Yeah, you can also call it operator, is this one. So if you meet this, if you see the symbol and you know already the meaning of P and Q, you know that the meaning of this compound statement, because this one class is simple statement. This is simple. You connect the two, you combine the two using this logical connective, which is called the end or the caret symbol. So it's raining and Daisy is playing golf. Isn't it easy to understand only? And then the or, so there, it's raining or Daisy is playing golf. The symbol for or is this one, right? And then the conditional. So if it is raining, then Daisy is playing golf. Okay. Then the negation, we can use the symbol class or the tilde. Remember the tilde? This one. We can use this or this symbol. Okay. It's not raining. Okay. So the truth value is you have to answer whether it's true or false, something like that. For example, it is raining. Is it raining today? So you know it's not, right? So false. So if you know Daisy, Daisy is playing golf. If you know Daisy, you know whether it's true or false. Question is, if one is true, the other is false, what is the answer here? Okay, that's what we will learn today. That is what I think the next slide has to do with that. Also, this one class, what if this is false? This is false. What can you see about the compound statement? Something like that. Similarly for the others. Okay, I think the next slide has to do with that. Oh, there, yes. So class, this is an example of a truth table. In general, but later on when we solve a problem, the problem in symbols, okay, because they're not problems in words, okay, so it's something different today. That's why for me this is a game, because you have symbols and that's like a puzzle to me. So for example, statement class, this is statement A. Simple statement A we denote as capital A. Then simple statement B we denote as capital B. So this is the, what do you call this again? This is and. This is the conjunction. This is the or. This is the disjunction. This is the if then. This is the conditional. This is the if and only if biconditional. This is what? Negation, the not. Okay. So if, for example, class, if A is true, okay, B is true, what can you say about this statement, this compound? If it is or and true also. Let's study one by one. This column. So if it's true, false, 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 true, false, 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 false. Okay, there's a pattern, class. Later we'll find out the pattern. Or let me tell you now, and then let's summarize later. So you will notice, class, that it will only become true if both simple statements are true. If both simple statements are true. That's why our statement a while ago, remember the end? Today is Sunday, right? False, because today is Monday. Tomorrow, and this is end. And tomorrow is Tuesday, true. So can you say about the compound statement? It's false because false, true, false. Okay, that's what you have to remember in the conjunction. This is conjunction, conjunction truth table. Only true if both simple statements are true. If at least one is false, the compound statement is false. Okay. Now for the or, opposite. It's the opposite. Now for the or, if at least one is true, it's true. The or, for example, true, true, true. Even if this is false, if this is true, true. False, true, true. But when will it become false? If both are false. So kind of opposite, right? Now for the if then class, it will only become false if this one. So you have to memorize that. TF. That sounds like tuition fee, right? Tuition fee, okay? So that you will remember. So because if you don't remember, if you don't pay at least 75% of your tuition, you cannot take the midterm exams. Okay, something like that. Okay, so that you'll be able to remember. Okay, so if it's TF, it's always false. Only true on the other cases, right? Okay, that's one thing to remember. Okay, you have to memorize this, class. You know why? This is like a pattern. Remember the compound statement, compound interest. We have a pattern, and we use that pattern to create a formula. So similarly here, these are patterns that you have to remember, to memorize. Okay, but unfortunately, we can only use logic to memorize this. I don't have, I can't give you any, as of this time, I wasn't able to create any mnemonic device for you to be able to remember, except the tuition fee, the TF. Okay, tuition fee. So if it's conditional, if then, you know already that if remember I call this in the if then, I call this the antecedent. If the antecedent is true, the consequent, the then part is false, automatic false, the rest always true. So in effect, if you're given if then statement or the conditional statement, you only have to memorize the TF. TF is always false, like that, or the tuition fee. So probably you have your tuition fee is wrong. You haven't paid the correct. That's why you cannot take the midterm exam, something like that. Or that's why it's restricted, because you haven't paid at least 75% of your tuition, something like that. That's why, that's the meaning. Okay, I just connected so that you will remember this. Now, the biconditional, class, you notice it's different from the others, because the others, among the four, there's only one, right? The rest, three. For example, 1 true, 3 false. This one, 3 true, 1 false. This one, 3 true, 1 false. Whereas here, you have two, just like negation, you have two true, you have two false. This one, you have 2 false, you have 2 true. Okay, what do you do with this one? Okay, it will become true as long as the same. True, true, true. False, false, false. True, something like that. The rest, always false. That's why you to remember this. For this one, class, it's easy to remember the negation. You don't have to memorize, of course, right? If the statement A is true, of course, the negation is false, right? Because, for example, today is Monday, true. Of course, if today is not Monday, that's false, right? You negate it, so false. So this is easy to remember. No need to memorize. Okay, it's just the opposite. Okay, now let's apply a problem on this. A problem. Oh, not yet. Actually, this one, class, I already mentioned to you what I mentioned on it. For you to be able to remember, for example, the conjunction of the statements P and Q is the statement P and Q, and it's denoted by this. So the statement this is true only when both P and Q are true. I mentioned this already. The pattern. When can you say that this is true? Only when both are true. Something like that. Or another way of saying it, if at least if in your simple statement, one simple statement is false, at least one, it's already false. Okay, that's one way to put it also. So I already mentioned this. Okay, no need to mention again. So let's have an example. Okay, this is the game now, class. This is what I'm saying, the game. Okay. So if you want, if you can use your Excel file also. But the thing is, you have the answers already, you have the answers. So later, anyway, later also I'll show you the answers. Anyway, so let us say the simple statement is denoted as P, and then statement Q is another statement is Q. But of course, we have really sentence there, right? For example, P is what? Something like today is Monday, and then the Q is tomorrow is Tuesday, something like that. So the idea there, class, is you have to use the pattern again that we studied a while ago. So you notice this one, not P. So you're referring to P. If this is true, this is false. If this is true, this is false. If this is false, this is true. Okay, by the way, class, how do you create this? Based on this, because we want to know if this compound statement is true always, if it's true always. But you will notice here, it's not always true. It depends here. That's why, remember, the truth table or the truth value of a compound statement, it depends on the truth value of the simple statements. And when you put all the combinations, we call this the truth table. Write all the combinations. Okay, by the way, class, how will you know the number of rows that you will put? How come 4 rows only? It depends on the given. How many statements do you have here? Basic statements, simple. You have like P and Q, or variables, basic variables, 2, P and Q. So you have 4. What's the formula, class? Okay, what if it's 3, PQR? You have 8 rows. Okay, what's the formula? The formula has to do with this. This one, did you see this? This one is raised exponent, just like in Excel file. Remember, we use this for exponent. This is 2 raised to n, 2 raised to n exponent. So meaning to say, if you have 2 variables, how many rows do you have in truth table? 4, because 2 times 2, 4. Now, if you have not only AB but ABC, what is 3? 2, 3, 2 raised to 3, 8. So you will have 8 in the truth table. 8. That's the meaning. 8 rows. Okay. So that's how you create a truth table. It depends on the number of variables or the number of simple statements in your compound statement, something like that. Okay, that's the formula. Okay, so now that's why these are just 4. These are just 4, no? So we have 2 2s and then 2 Fs, right? 2 false. Okay, so now we'll just how will you know the columns? If you have 2 basic variables, you have 2 columns for that. If you have 3, for example, R, PQR, you have to put the R. So to know the number, to know the columns, no? To know how many columns. Now, since you only have 2, so you have the 2 basic, P and Q, and then you have to look at this. You have what? Not P. You have to include that. The simple statements and the compound. I mean, the compound statements. These are the simple and the other compound statements. So it is compound, so you have to write that. Also this, you have to write so that you will know this one. What is the truth value of this? Then that's the last. So it depends on the problem. It depends on the given formula. The number of columns will depend on the formula that you have, because you have to write all the simple statements as well as the compound statements that you can find in the formula for the columns. Okay, now you know already how to find the number of rows and number of columns. Now let's go to the truth value of these statements, the truth value. So for example, if this is true, this one, class, you'll be the one to write it, and also this one. The combinations, all the combinations possible. So true, so you already know the pattern, right? If this is true for not P, false, true, false, false, true. Okay, that's it, not P. How about for the conditional, the if then? Remember, in if then, it's only false if you have tuition fee. TF, right? The rest true. Okay, that's the reason I want you to memorize those patterns, because it's easy once you apply here. It will be easy to write the truth value. So we know that in if then statement or the conditional, what is false only is this pattern, the TF. So false, the rest true. So now you can get the answer also by using that pattern. What is this, class? This is what? Conjunction and this is and. So in and, class, is this and? Oh yeah, there's something wrong here. No, because remember, in and, what do we get for and? Look at the and or the conjunction. Is it conjunction? Okay, let's see. Yes, this one. So if you will look at it, the and is Indeed, conjunction. It's called conjunction. Now, for conjunction class, the end, what is true is only the true. The others false. So only the true is true. Okay, let's see if it's correct. This one and this one. So true. So this is false. This is a I'm sorry. I'm sorry. Because this one is true. So true. Okay. So true. The true false is what? Is false, right? The true false is false, or the false is false. Okay, this is correct. I'm sorry. This is correct. Because remember, in the conjunction, if at least one is false, it's false. This is false. This is false. But this one, true. Okay, so this is correct. Okay, class, you understand how to make the truth table if you're given a certain formula. Okay, so that's an example. So now, what will happen if all of these are true? What do you call it? What is the statement? If all of these are true, what do you call the statement? If all of these are false, what do you call the statement? So that brings us to the next lesson, to the next terms. Tautology, contradiction. So a tautology is a compound statement S that is true for all possible combinations of truth values of the component statements that are part of S. So this component statement class are the simple statements. The S class is the compound statement. Now, a contradiction is the opposite of tautology, meaning it's a compound statement that is false for all possible combination of truth values of the component statement that are part of S. To know, just use that the truth table. You have to get the truth table. If these are all true, tautology. If these are all false, contradictions. In fact, we have an example. Okay, there. You have to show that this is tautology. Meaning, indeed it is, right? Because all are true. How will you know that? You have to create a truth table. How do you create truth table? So first, how many basic variables do you have? 2. So how many rows? 4. 2 times 2, 4. Now, how will you know the columns? So first, write the basic P and Q, and then the compound statements. So we have this compound statement, this one, and the last one, because that's what we want, right? And then just like what we did in the example a while ago, the same thing. So true, right? True, false. Remember, in conditional, true, false, that's false. The rest always true. False, true, false, always true. Okay. Similarly for this, right? Because this one is also if then, but it's the opposite. Q to P. If Q, then P. So find the TF. So false. The TF. So false. So the other rest true. So now this one class is what? What is this? This is disjunction. This is or. Remember the or? For the or, if at least one is true, it is a true statement. If at least one is true, this is or. So look at this: true, false, true, false, true. So see, so all true. So this is a tautology. Now, if you get all false, that's a contradiction. We don't have an example for that, but I think that's easy to understand. I believe you can do this, right? It's easy, right? So easy. Now let's go to part 2. Part 2 class is quantifiers. So this concept is also easy. It's just an easy concept. Universal quantifiers uses none, no, all, and every in a statement. Quantifiers none, no denies existence of something, whereas all and every asserts that every element of a given set satisfies some condition. Okay, let me explain this. I remember in part 1, the logic statement, we use the logic connectives, the and, the or. Okay, there's a similarity here. For this one, for us to be able to have a quantified statement, we call it quantified statement class, we use the quantifiers. The quantifiers class are the none, the no, the all, the every. So in other words, this is similar to remember the in English, in grammar, the indefinite pronoun. This is like indefinite pronouns, right? The none, the no, the all, the every. Okay. So that's the class similarity in part 1. Okay, so the quantified statement, you have to use all. For example, okay, every. Let's use that statement. If there's a statement with this, with the none, the no, all, and every, you have a quantified statement. For example, every Monday, how do you say it? Every student is required to take the midterm exam. Every student is required to take the midterm exam. So that's a quantified statement. Okay, you understand? That's a quantified statement, which is in a way a logic statement also, because it's either true or false, right? But we have a specific name for that. We call it a quantified statement, which is a simple statement, right? because we don't use any logical connectives. But instead we use quantifiers. So every student is required to take midterm exam. Okay, so that's every. Or all students are required to take midterm exam. So that's also quantified statement. Okay. If you want to use none, none of the students, okay, none of the students in section, for example, 146, okay, none of the students in section 146 took the exam. So that's also a what? Quantified statement. As long as you use this class, the none, the no, all, and every. Okay. So now, what's universal quantification? This class is also easy to understand. Universal meaning it's always true. So if you use the class, the all and every, so that's a universal quantification. Okay. So the universal quantification of PX is the proposition in any of the following forms, but we put it in symbols. But in a way, we can call it the process that we did to create that statement using the all and every is universal quantification. But we have to put it in symbols, something like that. So in symbols class like this, P of X is true for all values of X. Actually, not yet completely symbol, right? Because later on, this is the symbols. These are the symbols, okay? P of X is true for all values of X because we have to connect the mathematics, right? So mathematical logic, not only symbolic logic. That is why we have to use these symbols, and we apply this in mathematics. P of X is true for all values of X. So there's all, right? So you notice that's a quantified, in a way, quantified statement. And it's an example of universal. Okay, we use universal quantifiers, right? There. So that's a universal quantification. Okay, class? So for all X, P of X, right? For each X, P of X. For every X, P of X. Given any X, P of X. So you see, can you feel that? There's like the universality mentioned, right? Like the all, the every. Okay? Now, all of them are symbolically denoted by this. Now, we can put like this symbol, this one, for every, for all X, okay? The symbol is called the universal quantifier and can be extended to several variables, okay? But again, it's not only this, right? Because we also have none, no. But our focus is the universal. That's why we use this, okay, this symbol. Now, there's another kind. There's more example here. Another example. The statement for any real number, but this one class is more specific. For any real number X, we always have X squared greater than or equals to 0. Is true, right? For example, now this mathematical logic, which is a quantified statement, which is also a logical statement in a way. Look at this. You know real number, diba? You know real number X. So if you put real number here, it's always true. For example, 0. 0 squared is greater than equal to 0. You put 1. 1 times 1 is 1 greater than 0. You put negative 1. Negative 1 squared is greater than 0, right? Even if you put fraction, it's always greater than or equal to 0. Whether it's negative or positive fraction or negative or positive decimal numbers. Because when you say real number, there are a lot of them, right? There are a lot of them. Not only the integers, even the fractions, the decimal number. So this is always true. Okay, so this is an example of quantified statement where you use quantifier. What quantifier? For any real number. But symbolically, we can write it this way. This is more like a statement. But in symbols, we can write it this way, right? So for every, so we use this symbol for every X. This one is an element, right? We use this in set symbol, set notation. For every X, an element of the set of real numbers. This is, we can say this like this, okay, in statement. Or this symbol we can also use. As long as, don't forget this symbol class, for every. Okay, and so on. The second form is a bit wordy, but could be useful in some situation. Now, there's another kind of quantifier, which is called existential quantifiers. The other one is universal. So this one is more of like, instead of for every, there exists. Uses some and there exists, and at least one in a sentence. So the existential quantification takes one of these forms. So if the other one is for every, this one, there exists. There exists an X such that P of X. For some X, P of X. There's some X such that P of X. So in symbol class, we use this, right? There exists. It's like the E, the reverse one. There exists X, then such that P of X. In statement, but in symbol like this. So we just pronounce as there exists X such that P of X. So the symbol this is called the existential quantifier. It can be extended to several variables. Okay, class? So we have an example here. there exists a real number x such that x is greater than 5. So now this is like mathematical logic. Symbolically, we can write it this way. So what's the meaning of this class? So meaning, not all, right? They're only for some only, because this one is not true for what? It's not true for what? For negative numbers. For example, 0 also not true. 0 greater than 5, false. What else? Negative 1 greater than 5, false. How about positive? 4 greater than 5, false. So there exists a real number, some only. So that's the existential, not for all, just for some or even just one. Okay, that's the meaning of this existential quantification. Notice that in existential quantification, we use this symbol because this one is what class? And, right? We use this symbol instead of this. You notice and. Because not only x greater than 5, but we want x to be real number, because we can say x is an integer, right? But we want x to be real number. When we say real number, not only integers, including fractions and decimals. That's why we have to put the n. Meaning to say, both has to be true. This is true, this is true. So that the statement is true. Remember, the conjunction, if it's both true, then the compound statement is true. Okay, class? Now to summarize, so this is the summary of what we did. I think this is the last one. Yeah, just a summary. Conjunction is this one, and then true only when both P and Q are true. Disjunction, meaning the or, false only when both P and Q are false, right? And the negation, also tilde, opposite truth value of P. Conditional, false only when P is true and Q. The tuition fee, tuition, TF, is false. So that's false, right? And then there's another one, which is the if and only if, not mentioned here. Okay, the if and only if true, both P and Q are true, and then both P and Q are false, then that compound statement is true, right? For the biconditional. Okay. So now there are two ways to quantify. So this is also summary of part 2. Universal quantification and extensile quantification. So these are the important. They're written in the form of, this one is what? For every. This is the universal quantification. There exists x, okay, such that P of x, this is the existential. There exists, right, respectively. To negate a quantified statement, if you want to negate, negation, you can change this one to this one, and then this one to this one, and then negate the statement, something like that. Okay. So anyway, I think that ends week 12. So this is very short class. No, this is very short. Unlike the other the other topics, the simple compound interest and annuity. Okay. That's it for today. Thank you for attending. Bye.